Hello, students, and welcome to today's lecture portion where we are actually going to be talking about something that should be relatively important for you guys in the future here, which is batteries. And this is going to be a topic that especially the tech nerds in the crowd are going to be pretty stoked about, mainly because you guys are using a lot of things that have batteries in them. And so we're going to explain the process for them as well as kind of explain the general concept of how they work, how we recharge them, and how some of the battery technology is changing, especially with how we're starting to drive hybrid and electric vehicles. And this right here is actually the shell of, or it's a scaled down version of a Tesla vehicle. And what you see here is that we've actually have independent electric motors right here. And these electric motors are fully electric. They use a battery just like your phone uses a battery. But instead of having only one motor for the vehicle, a typical Tesla vehicle will have two or sometimes even four different drivetrains going on there to make the vehicle go forward. Okay. Now, the basics of this, of a battery, they are typically going to be called either a galvanic or a voltaic cell. Okay. And it's going to have at least one reagent that is going to be oxidized, and then you're going to have one reagent that is going to be reduced. Okay, and electrons are essentially going to be flowing from the 2 points of the system right here. All right, and both the reagents also cannot be in contact, and that's part of the process here. So what we're doing is we're essentially taking a redox reaction, okay, where we're taking the fact that one thing is having electrons move over to another object. So one reagent is gaining electrons and the other one is losing electrons. And what we're doing is we're taking that movement of electrons and convincing that movement of electrons to do work for us. Okay? So in this reaction right here, what you'll notice is that we have two reactions. One is going to be silver chloride, and this silver chloride is just going to be what's coating this stick right here. Okay? This is going to be what's coating the cathode side of it right here. And what's happening is that silver chloride is being reduced, which means that it's taking some electrons and it's turning into regular silver and some chlorine ions. On the other electrode, which is going to be our anode, what we have is we have cadmium. And this cadmium is losing electrons, okay? It's solid and it's losing electrons. And when it goes and it loses electrons, the cadmium actually dissolves into solution. Okay. So just like with this one here, you could see that the chlorine went from solid to being aqueous. The cadmium also is going that way as well. Okay. And so what's happening here with this is that the electrons are moving through the wire between these two electrodes, and they're going this path directly. And when these electrons move, that movement of electrons as they go around into this side here is essentially the electricity that we can convince to do work. Okay? So we're convincing these electrons to move, and that movement is how we get work. All right? Okay, and this is just further showing that the silver chloride, the AgCl, which is coating our cathode, which is going to be one of our new terms that we're going to want to also record here. Okay. Oh man. So, cathode is going to be one of our new terms, and it's going to be the place where reduction occurs on a battery. Okay. So, let me go ahead and add a slide here. And we're going to go ahead and write down cathode. And it's going to be the place where reduction occurs. In a cell. And then anode is going to be the place where oxidation occurs. Okay. These are going to be our two terms here for this one here. So make sure that you have both of those things down. Okay. And we don't really need to worry much about this one here for this one here. Oh, and it did have it there. I was just ahead of the game. All right. So again, oxidation takes place in the anode. Cathode is where reduction takes place. Okay. This is a typical galvanic cell. And what I want you to notice here about the galvanic cell is, first of all, that these two things are actually fully separated here right now. Okay. And what we have is we have some cadmium, and it's combined with cadmium nitrate. And over on this side, we have some silver nitrate, and we have a silver electrode right over here. All right. And what's going on is that this is another just example where we have an oxidation reduction reaction happening. Okay. And what's happening with this oxidation reduction reaction is that the electrons are leaving from this cadmium. They're moving through and they're moving over to this silver nitrate solution. Okay. What happens when these electrons get over to this silver nitrate solution is that the silver ions that are in the solution are going to turn into silver solid. And likewise, when the cadmium loses electrons, it is going to go into solution. What we have here is we have what's called a salt bridge. And what a salt bridge does is it kind of makes sure that we have an imbalance between these two compounds. And it makes sure that we have a charge and a way for the electrons to flow through. So as the electrons are flowing through and the silver is coming out of solution here, what's going to happen is that the potassium that's in here, that's in our salt bridge, is going to flow into the liquid here. And when that happens, it's going to help make sure that that liquid is doesn't have a charge, which makes it so that we can maintain our potential for a longer period of time. Because otherwise, what will happen is that some of these electrons will go over here and the battery will stop relatively quickly. Whereas, if we make sure that we have this salt bridge in here, it's going to equalize here. Okay. And as this reaction goes forward, what you'll notice is that we'll have some positive ions that'll come in through here, and we'll have some negative ions go in here. And here are positive ions are going to go into the salt bridge, and our negative ions are going to come out of the salt bridge. Okay. Okay. And this kind of completes the circuit in general here. Okay, one thing that you should also know is that we typically think of the anode as the negative end of the terminal and the cathode as the positive end. Okay, if you notice, the positives are flowing in, the negatives are flowing into this one right here. Okay, A shorthand way that we can go ahead and represent this cell is with making sure that the anode's on the left and that the cathode is on the right. And then we include like what the actual metal is and what the solution is. Metal and then solution. And then here, this is what the ion formed is going to be, and this should be the concentration. Okay. And this is how we do a shorthand notation. This piece of knowledge in particular is more so that if you do end up encountering it somewhere, it's not something that should be tested, but if you do end up seeing it later in electrochem, you should be able to be like, oh, okay, this is a shorthand notation for an electrochemical cell. And you should be able to then refresh your knowledge, because at least now you have the baseline, like, oh, okay, this is what this is supposed to be. Okay. Next, what we have is this is going to essentially lead us to what's called the standard potential of the cell. We're not going to go into this one in too much depth today because it's not required for this redox section that we have in ACE, and for pre-ACE this actually gets covered in a little bit more in depth. But this voltage is actually going to go ahead and come from both sides of our cell, and it's going to be from one side, the anode side's willingness to lose electrons, so how willing it is to lose electrons, and that's going to be added to the other side's willingness to take the electrons right there. Okay, and so those are just the two factors that affect what the overall voltage is going to be. Okay, so, and this goes just like way back to when we were talking about in particular the Gibbs free energy equation, where the amount of work that we can get done is. Here, this E part has to do, in particular, with the voltage or what compounds we have involved in our actual electrochemical cell right here. Okay. And then what you'll end up seeing is that we're also going to have a electrochemical cell table. And what this table has is it has all of the elements, a whole bunch of compounds that are essentially undergoing their redox potentials, and it will have their actual voltage right here. And the greater the difference between these, the greater the voltage of your cell is going to be. Okay. Now this is going to come to the part where we're going to go ahead and explain some of the long-term lasting effects of some of these things. And one of the things is that right now, something that's really big is that we are working on converting a lot of our fleet of cars to hybrid vehicles. Okay, and I have even switched over to a hybrid vehicle, and I have to say that in terms of the amount of gas mileage that I'm getting, it's great. And how a hybrid vehicle works is that it still has the typical internal combustion engine. But what happens with this engine is that this engine has a different role primarily in the vehicle than it did before. The engine's primary role is that it's actually to charge the battery pack here. Okay, so what you see here is you have a internal combustion engine, and it's connected directly up with the battery. And what it does is it just charges the battery. Okay, it's not responsible for its primary job is not to move the car, but it's to charge the battery. Okay, and then the battery is then connected up to individual motors, usually one on each wheel, And the battery then discharges to electric motors. And electric motors are usually a lot more efficient at using energy than an internal combustion direct line conversion ends up being. So what happens is that because of that, it ends up being a lot more efficient to charge the battery and then have the battery drive the electric motors for each of the wheels. Now, also, a lot of your hybrid vehicles are going to have a direct connection to two of the wheels as well, which makes it so that you can have a little bit more power during certain times. Often when you're driving a hybrid vehicle at 70 or 75 miles an hour, what you'll notice is that if you have a little display, it'll say that you're using a little bit more gas during that time. And the reason is that in order to keep it at that speed, to maintain that speed, it usually has to engage this internal combustion power drive system that's right here. Okay. And then also when you accelerate fast, you have to use that internal combustion engine. One of the jokes about electric vehicles was that they were really, really slow because the actual motors for each wheel doesn't actually have a lot of power involved with it. But, Tesla's been gradually changing that up, and we actually have some new electric cars that are going to be a lot faster than their internal combustion engine counterparts, because the technology is improving and there's other things. The other thing is that these cars end up being really, really heavy because the battery packs are pretty heavy. Okay, which will also lead us to the fact that we have a charging mechanism in almost all of our batteries now. Okay, and so essentially what happens with a charging system is that we're actually going to go ahead and convince the battery mechanism to go in reverse. So before, when we were going from anode to cathode, what was happening was that we were sending our electrons this way, okay? But what happens with a charging mechanism is that we actually send the current through the cathode, and we're sending pure electrical current, so we're adding current to it. And when we add current to it, we can force the ions that we had created before, and we can force them back to go the other way. So a battery essentially works by its natural state. It wants to go from anode to cathode. But if you add energy to it, what'll happen is that you can force the reaction to go the other way. And with a lithium-ion battery, that is how we force the lithium ions to go from one side of the cell to the other side. Okay, and then that's essentially how charging works. I believe for this section we're going to end up having a paper, and I think we'll probably actually do group presentations. And for the group presentations, what'll happen is that we'll have one group go ahead and explain this type of battery for the class going forward. We're gonna experiment with something else for this section. But as it is right now, this will go ahead and close us out for our battery lecture. For those of you that are in ACE chemistry, this should be a good review. For those of you that are in pre-ACE chemistry, this should be pretty new. Make sure that you're able to, from this lecture, identify the anode and cathode, analyze what's going on with the movement of electrons, how that's important, and know how batteries are essentially the thing that kind of drive us going forward in terms of new technology, especially for vehicles, and be able to explain that with some degree of knowledge, especially on the reduction potentials and how, the chemicals that we use in the battery kind of determine how well it, how much free energy that we can get out of it. But this should be mainly a term lecture, and as always, remember to stay lazy.